Hello everyone. So finally in this video, I am starting the backpropagation section of neural network from scratch playlist. And I promise you that after completing backpropagation from this playlist, you will have the complete mathematical intuition behind how this backpropagation actually enable our neural network to do such complicated tasks. Okay, so when I was going through the backpropagation section from the book, I was very unsatisfied by the way it was explained there. So at that time, I had gone through many other resources and spent lots of my time there. So the methods and concepts that I will be covering in this video and some of the few upcoming videos, you will not find those concepts in the book. So take it as prerequisites of understanding backpropagation. Okay, let's start. Here as you can see that I have taken the simplest neural network possible, and in this neural network diagram, there are two layers, layer 1 and layer 2, and each layer has single neurons. This is layer 1, this is layer 2, and this is the input that we are giving to our neural network. While we are proceeding, you have to keep two things in your mind. First thing is that in the whole neural network process, we are aiming to predict in such a way so that our accuracy is maximum. And this accuracy will be maximum when our cost function will be minimum. So overall, we are aiming to decrease this cost function. And the second thing that you have to keep in your mind is that this cost function is overall dependent on our weight and biases. So all we have to do is to adjust these weight and biases in such a way so that our cost function is minimum. So now let's see how this cost function is dependent on weight and biases. Okay, now see what this Z1 and A1 is representing. Z1 is representing the output given by this neuron after taking X0 as input, and A1 is representing the activated output after taking Z1 as input. So we can write Z1 as the function of X0 and A1 as the function of Z1. So look here, I have written Z1 equal to weight times input plus bias, and A1 equal to activation function applied to Z1. Similar thing I have done to Z2 and A2, and then I have calculated cost equal to A2 minus Y2 whole square. So here I have taken cost function to be mean square error. So in this one forward pass, our neural network is giving the output A2, but the real value is Y. So the mean square error will be square of A2 minus Y. Now, I think from these 5 equations, you must be able to get the relation of cost as a function of weight and biases. Suppose you have to get the relation of cost as a function of W2, then you will first replace A2 from this equation and then Z2 from this equation. By this, you will get the relation of cost as a function of W2. At the beginning of the video, I have told you that our final aim is to somehow decrease this cost function by adjusting the values of weight and biases. So now we will calculate rate of change of cost function with respect to each of weight and biases. So here I have written del C by del W2, and we can further expand it like this. And here you can see 3 terms are coming. These terms will get cancelled out and we will left with del C by del W2. We can further visualize these 3 terms from our neural network as well. Look, here we have calculated cost as a function of A2. And see, in the neural network, we had first calculated cost as a function of A2, then A2 as a function of Z2, and then Z2 as a function of W2. Similarly, we can calculate derivative of cost with respect to A2, and then del A2 by del Z2, and then del Z2 by del W2. Now we have to evaluate each of these terms. Del C by del A2. For this, we will use this equation. So del C by del A2 will be 2 times A2 minus Y. Similarly, del A2 by del Z2. For this, we will use this equation, which will give sigma dash Z2, and then del Z2 by del W2 will be A1. Here see, sigma dash is the derivative of activation function, and if we assume our activation function to be ReLU activation, then we can write our ReLU activation like this, and if we take derivative of our ReLU activation, we will get this. So this represents that if our ReLU activation take a positive input, then its derivative will be 1, and otherwise its derivative will be 0. So here if Z2 is positive, then sigma dash del Z2 will return a 1, otherwise it will return 0. And in that case, del C by del W2 will be 0. Similarly, we can calculate del C by del B2. And here you should observe that when we are calculating del C by del B2, only the last term will get changed. The first two terms will be similar to del C by del W2. So I have written 2 times A2 minus Y into sigma dash Z2. And if we evaluate del Z2 by del B2, we will get 1. And this is true for all the other cases. Whenever we calculate rate of change of neuron output with respect to its bias, we will always get 1. So now let's calculate del C by del W1. So we can further expand it like this. And if we evaluate all this term, we will get this. Then del C by del B1, only the last term will get changed, and all the starting terms except the last term will be same, and the value of last term del Z1 by del B1 will be 1. So overall we will get del C by del V1 will be this. So these are all the derivative values which we will get after each backward pass. And with the help of these derivatives, we want our weight and biases to get adjusted. So how do we adjust our weight and biases with the help of this derivative? And the formula for this is final weight equal to initial weight minus alpha into del L by del W. Here alpha is the learning rate. We will get to know more about this learning rate after we complete the backpropagation section. For this moment, just take learning rate as a parameter which will decide how drastically we want our weight and biases to get adjusted after each backward pass. Now let's analyze the working of this formula. Suppose after the backward pass, the value of del L by del W is positive. So this indicates that as our weight increase, the loss value will also increase. But we want our loss value to be minimum. So we want to decrease our loss value, and for that we want our final weight to be lesser than the initial weight. And here in the formula, del L by del W is positive, alpha is positive. So this overall term will get subtracted from the initial weight, and the final weight that we will get will be lesser than the initial weight. In the similar way, if del L by del W is negative, this indicates that our loss value will decrease as we increase our weight. So we want our final weight to be more than the initial weight in order to decrease the loss value. So here you can see del L by del W is negative, and the negative of del L by del W and this negative will become positive, and this overall term will add up with the initial weight, and the final weight that we will get will be more than the initial weight. Oh my god, guys, you are still watching this video. Excellent. I think if you had even understood 70% of the concept that I am trying to explain you, then I think you must have got a good idea of how this backpropagation works behind the scene. And if you are still not feeling confidence, then I will suggest you to watch a 3 blue 1 brown video. I will provide the link of that video below in the description. And even after that, if you have any confusion, then please comment down below. I will definitely try to answer your queries under few hours. Before ending this video, I want you to explain one more concept which is very important. I want you to realize that these all 4 derivatives which we have calculated depend on the input that we are giving to our neural network. Let me show you this. See, when we evaluate del C by del W2, it depends on A2, and we know A2 is our output. And this output depends on the input that we are giving to our neural network. So overall we can say that A2 is somehow depending on X0. So del C by del W2 will also depend on X0. Similarly, all these derivative terms has A2. So all these derivative terms will depend on X0. So this is what I was trying to explain you. These all derivatives depend on the input that we are giving to our neural network. So here comes 2 different scenarios. One, when our batch has only 1 sample, and when our batch has multiple samples. Whatever we had done before is applicable for the situation when our batch contains only one sample. But in the case when our batch has multiple samples, corresponding to each sample data, we will get different value of these derivatives. Suppose we have to calculate del C by del W2. Then corresponding to each of these three sample data point, we will get three different value of del C by del W2. And to apply this formula, we will take the mean of del C by del W2. This is very important. We will do similar with del C by del B2. So this is very important. Keep in your mind that when our batch has multiple samples, corresponding to each sample data point, we will get different values of derivative, and we have to take the mean of this derivative to apply this formula.